We're going to go ahead and get started. Steve wrote up the GitHub if you need the code. So I sort of thought I'd do a 30-minute sort of intro to the method and some of the basics. We're going to assume people don't know anything. So this is like the very introductory phase to MRS. And then we would like let people code and work on code for an hour. And there's some some practical slides, some questions, and some explanation of the examples in the code. And that's both a PDF of these set of slides and a PDF of that set of slides is also in the GitHub. Yeah. So, and I should say this is a workshop that I developed actually for another conference last summer. And Ricardo helped me a lot with that because it was the first time I was putting it together. And so, yeah, this is sort of like assuming we're starting with not even knowing what the Stokes equations are. So I'm assuming most people know a bit about fluids in here. But yeah, we're working with the Stokes equations, and I have things at both 2D and 3D. The practical part of this workshop is mostly in 2D. There is one 3D example for people to look at the very end if they're interested. And then Sarah and Dana in the second workshop are mostly going to be working in 3D, I believe. And so you'll have more opportunity to work with 3D this time. So I have all this information both in 2 and 3D for the basics here. Okay, so we're working with the Stokes equations. This is our conservation of momentum and our conservation of mass. In these equations, X is our position, Y is our force, or Y is our position of the force that's being applied. So X is where we're interested in the velocity and the pressure, and Y is where we're applying a force that's creating the flow that we're interested in. So the velocity is a function of X, and the pressure is a function of X, and then F is our force being applied on Y, and then mu is our viscosity of the flow. Okay. This is the exact same thing in 3D. Okay. I wrote these for sort of an introductory level graduate student. So like someone who's never seen these equations. And so a lot of it's done term by term. If you have any questions, please feel free to interrupt me. Okay. And so this is now assuming that X and Y are points in 3D, and then our velocity is also in 3D. Our pressure is a scalar, but the force is applied in 3D as well. Okay. And then because in the fluids world, we tend to write our equations with shorthand, these really translate into 2 equations component-wise, and this is what that looks like. Okay. And so we have our gradient of the pressure, and then our Laplacian of our 2 components of our velocity, and then our force being applied, and delta is our Dirac delta function that I'm going to talk about in a second. Similarly in 3D. And finally, I want to spend a minute talking about the force, because this is where the method of regularized Stokes slits, like the numerical component, comes into play on the force term, really. And so we have this force F times our Dirac delta function, because the force is being applied at the position Y. And so in 2D and 3D, that's how we write it. And the integral of the Dirac delta is 1. And then it's like the integral of a function times our Dirac delta is 2x. And this is where the time dependence can come into a problem, even though we're solving steady Stokes here. So if F depends on time or the location of where this force is being applied changes in time, you can now have a temporal component to your flow, and then you do have to time step. And I think it's like Sarah's not in here, is she? Oh, she is. You guys are doing some time stepping stuff in the afternoon? No, a tiny bit. Okay. Okay, and so now this is getting into how do we actually derive the solutions to the Stokes equation. And like in my intro graduate PDE class, we do a little bit of this. So you can solve by taking the divergence of the momentum equation and using the fact that the divergence of the velocity is 0. And then you can use the Green's function for Laplace's equation and the biharmonic. So this capital G is your Green's function of Laplace's equation, and capital B is your biharmonic here. And so using these, you can then write down your solution to the pressure first, which looks like this, and then the solution to the velocity here. And then this is just writing down exactly what G and B are in 2D and 3D. Okay. So this is your Green's function to Laplace's equation, and then your biharmonic in 2D, and then once again in 3D. And this is what I'll like to point out is that due to the log and the 1 over R, this is where we get our singularities. And I should point out, R is the distance between our 2 points, X and Y. Like I went through these slides yesterday. So this is more commonly the way this is written. So you can just plug in the Green's function and the biharmonic on the previous slide, and we call the Green's function for Laplace's equation the Stokes-Lit. And I've written this in Einstein notation because it's much nicer to write it in Einstein notation, and I think it's much more clearer. And here, delta ij is not your Dirac delta, but your Kronecker delta. Okay. And so this is a tensor. Okay. And then the solution of U now can be written this way, which is just the same slide. Okay. Are there any questions? Does this all make sense? Is this all review for everyone in here? A little bit. Okay. And then this is in 3D. So the exact same thing in 3D. Okay, so what is the method of regularized Stokes-Lit? So it's basically the same exact idea that I just went through, the same derivation, except now instead of using the Dirac delta on the right-hand side of the force, we're going to regularize it. We're going to smooth it out. Okay. And the reason we do this, and Ricardo touched on this morning, is that he sort of mentioned that he had that slide with the sphere, the curve, and the points, and that maybe we want to think about these things differently if your force is being applied on a surface in 3D, or a line in 3D, or a curve in 3D, or a point in 3D. And so the singularities are integrable if you're working on curves in 2D or surfaces in 3D. So things are pretty nice in that case. But challenges occur with these singularities when you have curves in 3D you're interested, or points in 2D that you're interested in. So where is your force being applied? If it's being applied on a curve in 3D or a point in 2D, you're going to have some issues with the singularities integrating them. And then even in the case where things are nice, so even if we're looking at a curve in 2D, so the images Ricardo showed today, you still have these near singularity issues that occur. So you have spikiness, even if it's not singular. Okay. And so this is one of the things that the method of regularized Stokes-Lit really helps with. And so the idea is, instead of using a Dirac delta function on the right-hand side as your forcing term, you're going to regularize it and smooth it. And it might look something like this, and this is called a blob in the MRS language. So instead of using a delta function, you're using a blob. And so this is, I was like, this is not the commonly used blob in 2D anymore, but this is the one that was in the original paper. Okay. And so that is the blob. Okay, and then everything follows exactly as it did for if you were doing a delta function on the right-hand side, and that's partly why I went over the derivation of the Stokes-Lit. So we've now replaced the delta function with phi epsilon here on the right-hand side. our blob is located at y still. We're still interested in the solution at x. So we're still trying to solve for the velocity and pressure at x. We once again can solve for this exactly as we did before. You take the divergence of the momentum equation, you get a Laplacian of p. The divergence of u is 0, so that term goes away. And you can use, once again, the equivalent of the Green's function for Laplace's equation in the biharmonic. But now, instead of having delta function here, you get the phi, so the blob, and then you get the Green's function here is what gives you the biharmonic. Okay. So it's the exact same process to do this derivation as it is to do it on the Stokes limit. Okay. And then you get that the pressure looks like this and u of x looks like that. One of the things when you do the derivation is that you are taking advantage of the radial symmetry of all of these. And so when you're working with the Dirac delta function, you're taking advantage of the radial symmetry, and you do the exact same for the blobs. So your blobs tend to be radially symmetric. I was like, I just wrote out taking advantage of the radial symmetry here. So then you can write it as derivatives of r. Okay. Feel like something, yeah, okay. So this was the blob that's in the original paper. And the solution in this case just becomes this. And it's messy to write down. But you can actually fully do everything analytically in this case. And then your capital R here is now, it's like the distance between x and y plus an epsilon. Okay, so epsilon is the width of your blob. It's a measure in your blob. So it comes in here. Okay. Any questions about this? Does this all make sense to folks? It's like, feel free to interrupt me. Okay. This is the more commonly used blob. So this is the one that over the years, people tend to use more frequently for various reasons. One, it's simpler to write down. So it's a simpler equation, but two, I was like, it has, I think, nicer properties as well. As I was like in error, maybe. I'm like looking at Dana and Sarah. They're going to talk about error in a little bit. So these are some various, but there are other blobs that one can use as well. In the code today, you'll have the option to switch between the two. And I don't actually know which one it's set to right now. And then in 3D, this is what the blob looks like. And this is from the paper from 2005, the original paper in 3D. Okay. So in all these cases, you can write down the pressure and the velocity analytically if you have a point force or a regularized point force on the right-hand side. Usually that's not the case. Usually you want to do something more complicated. So you might want to have a surface or a curve on which you're applying forces. And so you can discretize those in different ways. And on the next slide, I'll talk about discretization of a surface or a curve. But here I'm just saying, let's say you have figured out some way to discretize the forces that you want to apply, and now you have a sum. And because the Stokes equations are linear, things are really nice, and your solutions just add up. Okay. And right now, I'm just going to write down the velocity, but you can handle the pressure the exact same way. So we're going to assume we have n points at which we're applying forces. F is a force here, so or F sub k is a force here, and we're applying the forces at the y sub k's. Okay. And then we're solving now instead of just being interested in solving at one point, we're actually solving at m points at the j points. So we want to solve for the velocity at m points. Okay. And then you can write your solution as u of xj summing over the n points. And it's just the same solution as before. I added the slide because Ricardo asked me to. So let's say, so normally what we do is we don't actually think about a series of point forces that are being applied in some domain. We think of it as, I have a curve on which I know some force exists, and I know like sort of what that force looks like. And then I think about it as a discretization of an integral. So this integral would be of g of y of s. So y of s is the curve on which the forces are being applied. And then I really want to integrate. And so in this case, g is actually a force density and not a force. So it's a force per length in this case. Okay. And so from the previous slide, F becomes the GK times ds in my example here. And so what you're doing here is then you're going to discretize this integral as a sum with endpoints. And so the reason I sort of like this is important to emphasize is a lot of times there's a lot of confusion between what's a force and a force density. And I say this both as someone who's worked a lot both with regularized Stokeslets and immersed boundary. I think that's a common mistake that occurs. And it was a bug in the code when I first wrote it. So yeah, so paying attention to your units is really important. Okay. And then the other thing to think about when you're thinking about this discretization is, so really so far, you want to think about where you like, as a numerical analyst, where your errors coming from. And so far, we've had errors from just the regularization of the direct delta, if we were thinking of exact point forces. And now, if we're thinking about a curve, you're also introducing another error from the discretization. Okay. And so, any questions about that? Okay. So, this is just the equation I had on the previous slide. And the thing to note is now we can write this in matrix form. So we can go between our forces and our velocity. And so that's what we usually do. We rewrite it in matrix form as U equals MF. I've written it out here so people can write it out. And I've written this in, like, I attempted to write it in 2D with a little bit of ... for 3D. So I wrote it with my first component of my velocity and then my second component of my velocity. And my first component of the forces and the second component of the forces. You can write it in whatever order you want, of course, but this is how the code is written. Okay. And then these are the size of your matrices depending on whether you're working in 2 or 3D. Okay. I'm going to point out, you need to think about well-posedness. When, like, how many points do you need if you want to invert things? Okay. So you can go from forces to velocities or velocities to forces, but you do need to keep in mind the well-posedness of the situation. Okay, so we derived solutions to the Stokes equations.
So
yes.
Your mic went off.
My mic went off. Well, the battery died.
There you
go. Okay. I was like, is this a fixable problem? Okay, sure. Okay. So, yeah, I was like, what was I saying? Okay, so we had our solution to the Stokes equations before. Because we're working with the derivatives of the velocity, in the momentum equation originally, we can add a constant flow and it's still a solution. Okay. And so here what we're doing is adding both a translational constant flow and an angular constant flow. Okay. And then it's still a solution. So if I'm taking, because if we go back and think about what the Stokes equations are, you're taking the gradient of U. And so, or the Laplacian. It's like, yes, of U. And so if you're taking derivatives of U, then those are just going to be 0 anyways. So you can add any constant flow. Okay. So the solutions I gave you earlier sort of ignored this fact. Though in the original 2D paper, the solution that's given, which is the one I gave you guys, it's assumed that the constant flow is this. It's the sum of your forces. Okay. And it simplifies things a little bit. So that's the assumption. And in 3D, it's 0. And then our angular flow is 0. Okay. So the solution as given on the previous slide does make an assumption on what those flows are. Does that make sense to everyone? Any questions about that? Okay. Because this is where things get. Biologically, we do need to make assumptions about these flows. So biologically, we often want the net force and net torque to be 0. And so instead of having a freedom to choose our constant translational and angular velocity, we're going to use these two constraints to solve for our translational and angular velocity. And we do this by saying, so this is the same equation we had on the previous slide, but now I just stuck my translational and rotational velocity on this side. And then we say that we want our net force to be 0 and our net torque to be 0. And so we now have 2 more unknowns, but 2 more constraints, and we add those into our system. Okay. Usually when we're solving for our forces and we're providing the velocity, so if we're thinking about like a swimmer and we're interested in the flow around our swimmer, right? Usually we say our swimmer's moving like this. So I have my velocity of my swimmer. I'm going to solve for my forces on the body of my swimmer. And then I use those forces to solve for the velocity external to the swimmer. Does this make sense to everyone? Should I say that again?
Say it one more time.
Okay. I was like, if I can draw. This is going to be your last example in the code today. So I have a little swimmer. And then if let's say I know how the swimmer moves. So I have my discretization and I'm going to prescribe the velocity of the swimmer. So I can let's say I've taken a bunch of movies of my swimmer and I know exactly how it moves. And so I know the velocity of my swimmer. I am going to then solve for the forces at those points. And that's by inverting the matrix. And the xj's and the yj's are the same. So then I have my forces on the swimmer, and then I can solve for the flow, the velocity outside the swimmer somewhere once I have those forces. Oh. Yes.
The dots, the starting point would be you'd have the velocity of the dots.
Yeah, so I have the velocity of the dots. So you can imagine, I'm thinking of this as someone got a microscope and they took a movie. I can piece together the location, the position, or the velocity from that. And then once I have the velocity of the swimmer, I can then solve for the forces there. And then I can use those forces to solve for the velocity in the fluid outside the swimmer. Yes.
So this big matrix has at least a 2-dimensional null space, right?
It no longer does, right? It used to. So
That matrix does, right?
I'm gonna have to. Yes.
So I guess, and then you add these conditions on the next slide. So I guess my question is Are you envisioning actually like adding rows to this matrix? Like, how does this inversion work in practice typically?
Okay, hold on, I'm confused. That's your question.
I'll ask at the end. You might be getting to this in a slide or two, so.
Like, this is my last slide on
Oh, okay.
that. It's like, ask your question again.
So I guess just if you have these velocities, you're attempting to invert like a non or a singular operator here, right?
It's a square. It was a square matrix, and I kept it square by adding. Okay, so originally I had a 2D null space.
Yep.
And so we usually make some choice for the translational and angular velocity.
Okay.
So sort of like I showed you in the earlier part, there was some like choice made in the original paper.
Mhm.
And so that got rid of that two-dimensional null space.
Right. I guess my question is much more low level than this. Like, where does that actually end up in like the numerical linear algebra? Like, how do you implement that in
Okay,
practice?
so here, this is exactly what I'm showing here. So I basically ended up adding the translational and angular velocity into the right-hand side, and then into the left-hand side.
Okay.
Sorry. Yeah. And then we're adding in another, like you're basically adding in that the sum of the forces
Okay.
and the sum of the torques needs to be 0.
Adding variables and adding rows.
Yeah, exactly. At the same time. Does that make sense to everyone? So if I'm working with a biological system, I'm not going to have this 2D null space that the translational and angular velocity can be anything. I'm going to say that it's going to be solved for by setting the sum of the forces and the sum of the torques equal to 0. And so that adds 2 rows to my matrix, or actually 3 rows or 4 rows. And then it also adds the translational and the angular velocities into my unknowns. Okay. Yes.
I have, I think, a very naive question.
Yes.
So when you make this plot and you, let's say, calculate the force, discretize and all that, why do you have to use the regularized stocklet? Why can't you use the Austin tensor, let's say, right?
So
In just a,
if I'm working, okay, so if I'm working on just points in 2D, right, I have to be a little bit careful because the points are not, it's not integrable in 2D.
Okay.
If it's just a point,
yeah.
right?
Okay, but here you are, when you're discretizing this, I mean, you're gonna calculate this like in a computer, right? Or
Yes.
it's still analytical, right? So you can still do this, even if you're not going to calculate this straight at the 0 point, you know what I mean? Okay.
No, I don't. But it's like there is a problem if I want to do an inversion at the point itself, because numerically, even if it's not exactly the same, it's still quite singular.
Okay, I see.
Yeah. And so the computer, yeah, there is a singular problem.
Okay, I see.
Yeah. Did that answer your question? Okay. We can talk about it more. There are a lot of like, you have to be really careful with the thinking about the singularities. And this is sort of the slide Ricardo showed earlier, sort of addresses this depending on the case you're in. So it's like, there are ways that you can also handle this with singular integrals. And boundary integral methods do this. Other questions? Okay. So that's it for my introduction to the MRS. These are the 2 papers that are sort of the 2 main papers. The first one's in 2D and the second one's in 3D. Yeah, Thomas.
You say something about the matrix. Is it easy to solve? Is it dense? You just use like a CG, or how do you solve it?
Oh, I just use, since we're working in 2D in the code, I just did like with MATLAB's built in. But so it's dense. So it's GMRS. And this is actually what Ricardo was talking about in his talk. Like the benefit of some of the work we've recently done is that you get rid of having to invert a dense matrix. So this is why that was so nice. But you do have a dense matrix you have to invert. And like, depending on how large your system is, so everything I'll show today is like the very basic and very simple way to do it, but you can get it into fancy. There's is what I'll say. And my 3D code, now I don't remember what I did, but I'm gonna guess I just inverted and kept my number of points small, but you could also use GMRAS or yeah. Yes, Lisa.
We're saying that if you're applying forces and solving, a lot of the biological problems that people work on, you're modeling things through elastic forces, bending forces, and so on. So there's no inversion.
Right.
It's just a direct.
So if you know your forces, it's just a sum that you have to do. You don't have to invert a matrix at all. So it's a matrix multiply. Let me put it that way. Unless they move. Yes.
I was just gonna attach that question, question to anyone here, have people encountered ill-conditioned problems if your matrix gets really big, or things like numerical issues with this matrix?
I was like, I'm gonna let some of the others address this because probably I don't have all that much experience with method of regularized Stokes. Does anyone else want to address this?
The question?
It's if the has anyone run into issues where they've had an ill-conditioned matrix if it's too large? Yes.
So if you make your regularization size big, then the columns of the matrix, two columns of the matrix, could become very similar to each other because the blob is averaging things out too much, and that causes the matrix to be nearly or very close to singular. So that's one place where if you make your hello, if you make your blob size large, then the matrix will tend to become much closer to singular and give you trouble. If you make your regularization size small, it tends to become more diagonal or diagonally dominant, and it's less of an issue. That's one thing I can tell you.
Can I just follow up on it? Like when you say large and small, is that because you mentioned that there's two different areas? There's your regularization and there's your discretization of your boundary. So like when you say the blob is big or small, does that mean relative to like your discretization effectively?
Yes.
Okay.
And I believe Dana and Sarah are going to talk about error.
We're gonna talk about that.
Yeah, they're going to talk about your error between regularization and discretization.
Did I say it right?
Oh, yeah.
Like when I want to think about error in the method of regularized Stokes, let's like look at Dana's thesis. It's like, any other questions, thoughts, comments? Okay, so this is just the basic introduction for those of you who've never worked with this. I was like, let me pull up my the practical piece so you guys can look at. I can sort of show you. And these slides are in the on the GitHub as well as are the original slides that I just showed. And so here I go through, so in the GitHub, the code, there's a number of examples from the paper, both the 2D and the 3D. They're MATLAB codes. So I'm hoping enough of you have MATLAB installed. And if you don't, maybe you can look at your neighbors. But basically, it tells you which example it is. in the slides, and then it tells you the name of the file to run it so you can compare. And then it sort of tells you what it's doing. So in this case, it's setting a tangential force density to be this on a cylinder of radius 1, and then it computes the velocity in the surrounding fluid. And then you can, these are some things that I thought people could think about. So on each one, I do have us think about regularization versus discretization coming into play. So thinking about that. Remember, this was like for a workshop for grad students, so there's some things about playing with the plotting and getting comfortable with some of the notation. I plotted this both in 1D and 2D. I tried to recreate the plots on the paper, but then also looked at other things as well. And so you guys have that option. But there's several examples, and I actually show you what it looks like here. So if you're not interested in running the code, but want to look at things, you can do that. And then some like sort of more sort of thoughtful things to think about or more complicated things to code up for each example. And so there are, I think there are 4 examples that I've done in 2D here. And then this is not, I have a swimmer, that's this example that I sort of talked about. That's not an example in the paper, but it's nice because you can see something time dependent where here, I'm setting a velocity on the body and the flagella, and then it computes the forces on the swimmer and then computes the velocity in the fluid. And so I thought we could spend the rest of the time playing with code, and Steve and I can walk around and answer questions if people have things they want to ask or think about. Yeah, so that's all I have for you guys today. And I was like, Dana and Sarah, you guys are doing a 3D sphere example.
Some 3D stuff, yeah.
Okay, so in the 3D code in the GitHub that I have, it's just one example from the 3D paper. It's the section 4 example 1. I believe it's forces on a sphere computed velocities, if I remember correctly. And so if you want to look at that 3D as well, that's in the GitHub over there. Okay. So this is, yeah, also the same references and acknowledgements here. Okay, thank you. Yes.
There might be people that never seen the method. Would that be helpful if you download at least the one example? What you just list out? Sure. One example.
Would it be helpful for me to run through an example?
Yeah.
Sure, I can run through an example. It's like,
If they're not the same problem.
I'm like opening my MATLAB. It's going to take a second.
Based on that size, you know, like I was using, I was using 1.66 or whatever times the S.
Yeah, I'm going to share my whole screen. We'll see if my MATLAB.
Yes.
There was fine. I ran.
We can just work through, it's like we can work through the first example. We can work through the first example. Now let me open. I was like, let me tell you about the first example. No, okay. So the first example is setting forces on a cylinder of radius 1 and then computing the velocity in the fluid surrounding that cylinder. So we know the forces, so we're not doing the inversion of the matrix here, we're just computing directly. If you know the forces, what is the velocity? And so this is main example 4B. So if we go to the code, that one, can you guys, this looks gonna be big enough. Is that big enough to read? That can get bigger, people in the back. Good. Okay, so we can sort of look through this. So we're setting the viscosity. I just set it to 1. And then I'm going to set the domain on which I'm interested in solving the velocity on. So I was like, I'm going to guess this is I'm solving on the domain 0 to 2 and 0 to 2. My forces are going to be applied on 100 points on my circle. So this is the number of points that I'm working for. And then I need to like set the points at which I want to solve the velocity. And so I'm going to do an 80 by 80 grid on which I'm going to solve the velocity for. Okay. So in the slides, if we go back and look, looks like my Zoom stuff is in the way. Okay. Let me open. I was like in our matrix here. I'm in the case where I am here and I'm working in 2D. And so in this case, my M is an 80 times 80. It's the M points that I'm solving for the velocity on. And N here is the 100 on the circle. Okay. I discretize my cylinder using the N points. I am setting my epsilon regularization parameter here to 1/4 of my discretization length. So I am building a relationship between the two. This is the cylinder on which I'm applying my forces. So these are the positions of where the forces are being applied as Y. And it's a radius, it's a circle centered at 0 with radius 1. And then I need the tangent of my cylinder boundary. So I can. This is the force that I'm applying. So remember that in my formulas here, over here, that things were forces and not force densities. And so keeping that in mind, I had to multiply, and I've like lost my MATLAB. Hold on 1 second. Let me move this part. Okay. So the force density is what's given in the paper. So I need to multiply by my radius times delta t to get it to be a force. Okay. And so these are going to be the forces that I'm applying on my cylinder. I'm basically just making this into a nice mesh that I can work with. So these are the points at which I'm interested in solving that 80 by 80 grid on which I want the velocity. Okay. And then this is where all the magic happens, is this function. So we can look at that. So I'm going to put in the point set where my forces are, like the position of my forces, and then where I want to solve for the velocity, my epsilon, so my regularization parameter, and then my viscosity here. Okay, that's my inputs, and it's going to spit out the velocity for me. And so if we go ahead and open that code, it's like we're going from force to velocity here. Okay. So we can see what we've done here. And so you can see that the Y are where my forces are located. F is the forces, X is the target points or where I'm solving for the solution, and U is the velocity at that solution. Mu is the viscosity and epsilon is the width of the regularization. And I try to keep the notation somewhat consistent with the slides here. There's just a lot of unpacking and repacking in these functions. So that's the first step, is to unpack everything into the 2D set of things, and then initialize the velocities that I'm going to solve for. And then I wrote this as a loop. So I'm just looping over my source points. I have to compute the distance between my target and source points, and then we add in this epsilon squared. So this is the capital R that was on the slides here. It's the distance between X and Y, and then my plus the epsilon. Okay. So it's that R epsilon in the slides. So it's exactly, let me go back to be like, you guys are gonna have to give me a second to find it. Yeah, so it's exactly this is all. Okay, which pops up everywhere. So it's nice to like have it computed. Okay. So we're gonna, so when you write out the sum here, let me go back. When you write out, like if I write out U here, I get two parts that pop out. And this, the part in the parentheses here, depends on my regularization function. Okay, so which function did I choose for phi? And so we're gonna feed in R and then spit this out depending on which regularization function I want to use, which phi do I want to use, okay? And so that's exactly what this code does. It spits out those two components, the A and B are the two parts. And so if we go and look at that function, it, I believe, has a couple of options. It should have the two options that are given here. And so you can see that right now the more commonly used blob is what's uncommented. And then otherwise it's the one in the paper if you want to use that one instead. Okay. And so it spits out the two components and all it needs is that R epsilon and epsilon to compute those two parts. Okay. Any questions about this? Does that all make sense? Yeah, so then once I have A and B, I can compute the U, the two components of U. And so, and then I need to divide by 4 pi U. And then I send it back. So this is going from the force to the velocity. The velocity of the force, instead of going through a loop like this, builds a matrix in the loop and then does the inversion. Okay. So it's the exact same functions that's being computed. It just has to build a matrix and do the inversion. Okay, so once we have our velocity, we basically unpack and resize everything. I've coded up the exact solution for us here, which I believe is given in the paper. And then compute errors and do some plotting. And so we can run this, and I was like, hopefully it's going to work. Okay. So let's see what our are you guys? It's like, you guys don't see my Zoom bar that's like floating around everywhere. Okay. So this is the red here is the forces that were computed on, that were the forces that were applied on the boundary. And then the black is the velocity that's computed from those forces. This is what the exact solution looks like. So they look quite similar. And then I just showed the error in magnitude and the velocity. And then I think this is going to be a Kuiper plot of the same thing. Yeah. So you can see that there are large errors close to the boundary due to the regularization. Any questions? Yes.
Sorry, so for the plot forces and error magnitude in the velocity, the color bar is the size of the error? but.
I'm gonna guess it's a log plot. Give me one second.
Okay.
Figure 4. Log 10.
Yes, it's a log plot.
Okay.
Yeah.
That makes sense. Thank you.
Yeah, no worries. Yes.
Also, if you go back to figure 1, I think forces
Fi-
in the computer velocity.
Figure 1, this one?
That one, yeah.
Yeah.
So the swirling flow there's no ambient flow, right? It's all due to the.
It's all due to the forces on the,
Oh,
yep. So, this is a case in which we knew the exact solution. And so the forces we're applying result in this flow.
I have a question. I know
Yes.
the answer, but I think it's a good question.
Yes.
In your plot form, you have log 10 error 1 plus X. Why have you introduced a new X? Well, we already had X.
Where are you looking? Oh, this is,
This is a rabbit hole for everyone to avoid that I fell into one time when trying to look at differences in regularizations.
Epsilon just adds machine precision. And so it makes things positive. Yes, it makes things positive. Which is,
Name your regularization X too. 'cause it-
yes. Yeah, so don't overwrite that. X is the MATLAB built-in machine precision. And so a lot of times we add it just to have something that's non-zero. So I always call my regularization EP, I believe. X is a built-in. Yeah, command. Other questions? Yes.
Can you go back like how you go from the force density to force?
Yeah. So I multiply by rho dt.
Let's just generate by default.
Length for the line
So
segment.
it's the arc length of the discretization. Yeah. And in this case, rho is 1, so I multiply by dt. Yeah. So there's no rho where I'm multiplying. It's just times dt.
But there's no.
Yeah.
One more basic question. If you can go to any of the figures.
Yeah.
The black circle is like one segment of the part of the swimmer.
It's one. Okay, so I should have been careful about this. I'm just plotting from 0 to 2 to 0 to 2. So I'm only plotting one quadrant. But you could also modify the code to do like -2 to -2, and then you'd see the whole circle.
But it's a circle at the head of your diagram.
Yeah. So
Okay.
I just have a circle. And so even though I'm only showing one quadrant, the solution that I'm seeing in the domain is due to the whole circle. Okay. Any other questions? Yes.
One naive question about the physics here, right? So you have a circle and you impose tangential force. So basically it's like you try to rotate the
Yes.
circle, right? So what would you expect about the fluid flow? Like in general, should the flow go around like this? Yes. Like,
So it's it's incompressible flow still, right? So I was like, the exact solution is figure 2 has the exact solution. So it still looks like this, but it's you have to think about it carefully because the force that's being applied you can see here, it has parts that are in this direction and parts that are in this direction. Yeah. So so you have to you have to think about it.
yeah, I was thinking like it's
This, yeah. So this is why you're getting, does that make sense? So the force we're applying is cosine and sines. So you get both directions. And therefore you're gonna get a flow like that.
More interested in flows. So we talked about the volats with the ciliated on surface. If you give it a really weird shape, then you miss the rotation because you don't have the extra constraint, which is why then you add on that extra torque constraint so you can get rid of that. And you sort of have to choose forces that necessarily don't rotate it.
It doesn't care about the boundary at all.
Do you guys want to see the swimmer? Because I didn't put the movie on the slide. I can show you guys the swimmer, which is a time dependent flow and not one of the ones in the paper. Okay, so we can just play it. But this is the example that does this. So let's see.
It should.
But the point is, if you don't.
This shouldn't talk to that.
Okay. So I am prescribing the position of the flagella and keeping the head still. And then I'm in the reference frame of the swimmer. So the swimmer, in this case, I do set the constraints. So I am also solving for a translational and rotational flow. And then I like move things so that it's in the frame of the swimmer. And so we don't see that in the movie. So let me play this again, or I can play it longer. I guess I don't know how long I have it set for. We can do it for like 100 time steps and stuff.
So can you sheet? Double nothing to do with it.
And I believe I was like, I need to look at what I'm plotting here.
You can't.
The color here is the magnitude of the flow, and then you have streamline. So what that looks like. But that's doing this case where you're using both sort of the forward and the inversion on them
It works for
in each time step. Any other questions, thoughts? Yes.
So for this swimmer, instead you already changed the frame so that it's in the swimmer body frame.
Right, it's in this one.
Still moving around, but the head will stay put.
Yeah, so I put that, okay, this is like one of the challenging things, right? It's like, you sort of have to get your frame of reference, right? And so in the code here,
Can square.
it's like, so I just wanted, when I wanted to prescribe things, I wanted to prescribe how the flagella was moving. And I knew it was a biological system. And so I needed the sum of the total forces to be 0 and the sum of the torques to be 0. And that's going to give me constraints on what the translational and rotational velocities of the swimmer can be.
But in the plot, you subtract the
Yeah, and so then I subtract. Yeah, exactly. So what you can see in the code here is, okay, here's where I solve for the forces and I get back out a translational and a rotational velocity of the swimmer. And then I compute the velocity on the grid and then I change the frame of reference here of the swimmer. So I subtract that out, the translational and rotational velocity that I've solved for.
So also for the head,
Yes.
you describe only on the surface, which is circle, right?
Uh-huh.
You don't need to do anything.
I don't do anything.
It's only checking the surface.
Uh-huh. Correct. Yes.
Since you have larger errors near the boundary and now you're doing like a time evolution, how long can you run it till you start to see the non-uniformity of the errors kind of propagate and distort the whole picture?
I don't know because I haven't run it that long, but you can. I was like, you can play with it a little bit. I actually haven't tried to run it that long. I don't know if it
It's
will.
quite a thin layer of the larger errors, so I don't know if you run it because your each time step is being based off the previous.
So I'm not sure it's an issue.
Okay.
I would have to think about that a little bit. But I don't think it's an issue.
They based on the figures? You know what the flagella is going to be.
Right.
Yeah, I think they're worked out independently at each time step because you know what the flagella is, and you know.
Oh, is it not the, because you're starting with forces and then you're calculating velocity? Oh,
So in this case, I'm prescribing where the flagellum is. I compute the velocity on the flagellum,
uh-huh.
and then
That gives you the force.
that gets me the forces. So I do my inversion to get the forces, and then I do a direct calculation. So there's no dependence on this time step here.
Okay.
I think if it's a free swimmer, it's gonna have some swimming path and you'll have some error then in the path because that's being integrated over time. Probably not a huge error unless it's a pretty crazy swimmer. It's gonna probably be a helix, typical helical path. So you maybe get that a little bit wrong.
Maybe so. I guess it would, if you time stepped the other modeling, then you might have that kind of issue.
What's the other model?
The one where you were going from the forces to the velocity, and then that generates new forces. If you do it that way.
Because you get new velocities and then you get. I guess, yes, if you're using forces to compute your velocities and then the velocities are. But if you have your forces, you wouldn't compute your velocities to get, like if I have my forces, I would just use those to get the velocity wherever I want it.
These are forces. Yeah.
Yeah, like I wouldn't do like the inversion then. And this is what Lisa was saying, right? That they often don't even, like if they know the forces, they can do a time development of the forces and then solve for the velocity wherever they want. And they don't have to do an inversion at all.
Okay, so I've got it backwards. It's the other way.
Yeah, so if
Not
you
the velocities,
describe-
you want the forces.
Yeah, and that's what I'm doing here, but it's like each time step is independent.
Okay.
Yeah.
Okay. And that's because you're prescribing the shape.
Yeah.
Okay. But if you weren't prescribing the shape and you were letting it evolve.
Yeah, so if I had something that was somehow the velocity was coming from something that's time dependent, then they propagate.
Okay, that's
Yeah.
okay.
Streamlines you work out.
I need to look at that.
Sorry?
So if you describe forces in the shape,
Yes.
we're interested in some point far away, and you want to integrate the force, the velocity at that point over time.
Right.
It's getting a contribution from
From-
each step over time, you might get problems.
Yeah, that's what we're saying. That it's like if you're doing a trajectory. Yeah. So, yes. Any other questions, things you guys would like me to look at, show you? Etc.
I have
Uh.
a general question that may not be related directly to the talk.
Okay, sure.
So let's say I'm running a PD solver that does all these stuff under the hood. Is it a good approach to still use the same blob function and discretize the boundary and just put it in the differential equation?
Say this again, you're using what? Sorry.
Yeah, let's say I'm using a PD solver that does this matrix inversion under the hood.
Uh-huh.
And I was just asking, is it still a good approach to use these blob functions as my boundary to say,
I mean,
imitate the swimmer?
yeah, so I think it depends on the problem you're solving. So sort of like Ricardo was talking about, it sort of goes back to, so I think you can use these blob functions if you're trying to do like a point force in 3D or like thinking about a curve in 3D. Like it will, if you're using sort of a generic PDE solver, with these blob functions, it should work fine because you are regularizing, so everything's smooth. So I was like boundary integral methods and boundary element methods, and there was someone here, now I don't remember who works on boundary element, right? Yes, so some folks, but those tend to like deal with the singularities more explicitly in different ways. And so like, I think at least I have more experience with boundary integral methods. They often choose their integration methods for singularities if there's a singular issue, vice versa, like how to handle that singularity. And that becomes a little bit more specialized if you want to do stuff under the hood.
Okay.
Yeah.
Okay. Thank you.
Not mutually exclusive.
Yeah.
I just use the regularization with boundary elements to do the integrals, and numerically you just no problem then.
And regularization, just like mathematically, is used for a lot of times when you have something singular that you want to handle numerically. So the immersed boundary method uses regularization in a slightly different way, and they'll talk about that in the tutorials tomorrow. So I think a lot of times regularization is, I would just say, used a lot when you're trying to deal with singularities in a numerical framework. I don't know if other people want to say more about that, but that's like been my experience. It shows up in a lot of places. And I think the trickiest part is, at least for me, has been thinking about, like, in each context, you often have to think about the error slightly differently depending on the formulation and the derivation. Yeah. Anything else?
Just like in general, like let's say like if you have a fluid flow, right? Let's say you have a shear flow. Like on the top, the flow goes this way, bottom the flow go this way. And if you put the particle in the middle, you would expect the particle to rotate due to Jeffrey orbits, right?
Yeah.
So how would you set that up in using the method of Rayleigh Stokes in order to stimulate that, rotation of the particle?
I have to think about this for a second, because you want. Okay, so
just motivates. I think. So basically the particle is passive, right? There's no force on that particle.
Yeah, so I was like, the way I would think about it is that you basically have two boundaries, and I would discretize these and set the velocities. Right? And then you can just put a grid in the middle, solve for your velocity over your entire domain, and that will give you the flow, and that should give you your rotational flow. Right? And then you want to put an object in the middle. And I'm like,
calculate for a circle in the middle.
Yeah.
Keep track of where the points are in the circle as you infect it through in time, and then you just look at like how they're moving all the time.
But yeah, that's sort of what I was thinking. So then you have a set of points here, and you just keep track of those points. You compute the flow at each one, you move them each time step. So now you're going to add a time component.
So somehow you have to be able to solve for the fluid flow in the surrounding of that circle first, right?
Well, you don't have to, right? So if you're only interested in your object, right? This is where I think MRS is like, so Stokes is much nicer than Navier-Stokes because it's not, right? So let's say I have some squiggly object here instead of a circle, right? I can just keep track of one point. And so I set up my velocity here, I invert, get my forces. That's the first step.
Yes.
So I get my forces on the boundary.
Well, but I mean, here you have fluid flow on the two boundary.
Right.
But we have to talk about the fluid flow also in between the two boundary too, right? You need to know the fluid flow.
So you don't need to know the fluid flow. That's my point. So, okay, so you have your velocity. So let's say this is u equals 1 and u equals, right? And so I set u equals 1 at the x's and u equals -1 here. I solve, the first step is to just put in these like 10 points and solve for the forces on the boundary. Okay, because Stokes' flow is not time dependent, like it's steady Stokes, right? That inversion only needs to happen once.
Wait, so you recommend to, okay, given the fluid flow on the two boundary,
yeah,
solve for the forces at those points,
right?
And then using those forces to calculate the velocity on the structure.
Yeah, so the velocity on this point.
But then the issue, right? Because the only forces on the two boundary, not on the whole domain in the middle.
Right.
But in reality, when you have Jeffrey orbit, I think
you have an object. You want to set.
Oh, right.
You want. I need to think of So you want to have a solid object.
Right. So imagine when it rotates.
I know, you're gonna get a flow. Okay, so you need another boundary, hold on. And it's a no slip boundary condition, right? So that's gonna be your velocity. Because it's not a passive.
Yeah,
Yeah.
most of the problem we're dealing with, we have an active.
Right, we have an active, yeah, so.
But now what happens if we have a passive
Passive.
structure and the flow is the one that drive the structure?
You need to set the velocity equal. The constraint is the velocity is equal to the
Greatest.
because I would cheat. I would do it because it's a rigid body. You know, it only has a translational. It's a rigid body rotation, so you can write it as a rigid body rotation. Yeah, there's a piece that can come into play like that, so that I don't have to disregard the boundary. Yeah, I need to think about it for a second, but I do think that, yeah, that's how I would handle it. Does that help?
Yeah.
Yeah. Okay, yeah, I need to think about it a little bit.
Yeah.
Can I answer other questions?
I remember.
And then if you guys are working on stuff, like Steve and I can walk around, look at code, etc.